Hello, today we're continuing in our series on GCSE physics revision and we'll be looking at potential dividers. In our video on series circuits, we learnt that if you have two resistors, R1 and R2, in series, then the total resistance in the circuit is just the sum of the two resistors. So it's R1 plus R2 is the total resistance. And then you would say that if this is a voltage V, you use Ohm's law, V equals IR. That means that I is equal to V divided by R, which is equal to V, the voltage, divided by the total resistance, which is R1 plus R2. And that gives you the current, which is flowing in the circuit. But we also said that this voltage is also called potential difference. We said that this voltage is dropped across each of the resistors. And the voltage drop, or the potential drop across each resistor, is the current going through that resistor times the value of the resistance. In other words, it's Ohm's law. So in other words, the potential drop across R1 is equal to IR, and that is equal to I, the current, that's I, times R1. The potential drop across R2 is also IR, that's IR2. So the potential drop across an individual resistance is simply the current going through it multiplied by the value of that resistance. Let's suppose that V is a 12-volt battery, that R1 is 6 ohms and R2 is 6 ohms. Well, in those circumstances, we first need to work out what the current is. So V equals IR means that I equals V over R, which is 12 divided by the total resistance in the circuit, which is R1 plus R2. 6 plus 6 is 12. That's 1 amp. So 1 amp is flowing through this circuit, 12 volts here, 6 ohms, 6 ohms. And what we want to know is what is the potential drop across R1? And what we've said is that that is going to be equal to IR1. Well, in this case, the potential drop across R1 is going to be I, which is 1, because we just calculated that as 1 amp, times the value of R1, which is 6 ohms. So it's 1 times 6 is 6 volts. And the potential drop across R2 is equal to IR2, which is 1 times the value of R2, which is 6 ohms. So that's another 6 volts. And the two lots of 6 volts add up to the 12 volts of the battery. So what we're essentially saying is that we've got a voltage at this is a 12 volt, and at this side you've got 0 volts. That's why it's called potential difference. There's a difference in the battery. There's a 12 volt potential. It is truly potential energy. It's usually chemical potential energy within the battery that makes a potential difference of 12 volts. So you've got 12 volts on this side and 0 volts on this side. So in other words, the potential at that point is 12 volts, because we'll assume that you don't lose any potential as you go along in a copper wire. But as you cross this resistance here, you have a potential drop of 6 volts. So you drop from 12 volts to 6 volts. And then as you go across R2, you drop by a further 6 volts. So you drop from 6 volts to 0 volts, which of course is the value at this side of the battery. So you've effectively gone from 12 volts to 6 volts and then from 6 volts to 0 volts. And therefore the difference in each case is 12 minus 6, the difference, the potential difference, 6 volts. From 6 to 0, potential difference is 6 volts. Now let me redraw that diagram on its side, because that's the way it's usually presented. So here's the battery, which we'll say is a 12 volt battery. Here is R1, which we'll say is 6 ohms. Here is R2, which we'll say is 6 ohms. And what we've just said is that this point here is at 12 volts. You drop 6 volts across this one, so this now is 6 volts. And then you drop a further 6 volts across this one, and so you're now at 0 volts. And what I want to know is, if you take a line, in other words 2 wires, from those 2 points, you join them at those 2 points, and you put a voltmeter across here, what voltage will you read? Well, the answer is quite simple. It's 6 volts. You're measuring the potential difference between 6 volts and 0 volts. So you've effectively got 6 volts coming out of here, which means that you could put a filament lamp that is rated 6 volts across there and it would light up. If you put the 6 volts bulb or filament lamp across a 12 volt battery, it would probably burn out. So this is a way of taking a 12 volt battery, and we'll call that the input voltage, VI, and getting an output, which we'll call VO, the output voltage, of 6 volts. This is a way of stepping down the voltage by taking out the voltage you need from a battery whose, as it were, voltage strength is not what you need, it's too high. This is a way of getting an output voltage that is lower than the input voltage. But what happens if we take exactly the same diagram, but this time we vary the values of the resistors? So this time this will be 8 ohms and R2 will be 4 ohms, and then we continue here and we take our outputs once again here and we measure the output here, V. Well, you can, I think, see without me doing too much maths that once again, if this is a 12 volt battery, the total resistance in the circuit is 12 ohms, 8 plus 4. The current is voltage divided by resistance, so it's 12 divided by 12. So once again, the current I is going to be 1 amp. And now the potential drop across each resistor is the current times the value of the resistor. So the drop across the R1 is going to be 1 times 8, which is 8 volts. The drop across R2, which is 4 ohms, is 1 times 4, that's 4 volts. So the voltmeter is going to measure 4 volts. And that means that you can put a 4 volt filament lamp here and it will light up. So you can get the output voltage you want by having the appropriate array of resistors. So now we better do it for the general case. So now it's just going to be the input voltage VI going through R1 and then R2, and we're going to take the output voltage across R2. So that's the output voltage VO. There will be a current flowing through the circuit, and what we want to know is, what is VO compared with VI? Well, once again, you start off with Ohm's law, V equals IR, so I is equal to V over R, and that's going to tell us what the total current is. The total current is going to be VI, because that's the input voltage, divided by the total resistance in the circuit, which is R1 plus R2. R1 plus R2. Well, what is the potential drop across R2? Because that's what we're interested in. That is going to be our output voltage. So the potential drop across R2, which is one and the same thing as our output voltage, is going to be the current times the value of the resistance. So that's going to be the current I times the value of the resistance R2. But the current I is given by this term here. So that's going to be equal to VI, the input voltage, divided by R1 plus R2 times, R1 plus R2 times R2. Or I can just rewrite that just with a slight difference, that VO, the output voltage, equals VI, the input voltage, times R2 over R1 plus R2. So depending on how you choose the values of R1 and R2, you can get different values for your output voltage. Suppose, for example, that the input voltage is 12 volts, but I want an output voltage of 2 volts. How might I achieve that? Well, I've got 2 is the output voltage, equals 12 into a certain amount. What does that amount have to be? Clearly this fraction must turn out to be 1 over 6, because 12 over 6 is 2. So I need to get 1 over 6. You can do it a number of ways, but an obvious way is to set R2 to be 1 ohm, and then you've got R1 plus R2. Well, R2 is 1 ohm. I want that whole fraction to be a 6. So what does R1 have to be? R1 has to be 5. So if R2 is 1 and R1 is 5, then I get that 1 over 5 plus 1 is 1 over 6. 12 over 6 is 2. So by choosing the right values for R1 and R2, I can get any output voltage I want up to the value of 12 volts. I can never get, under this arrangement, anything higher than 12, but I can get lower than 12. So here's an exam question. We have a battery at 9 volts. We have a resistance R1, which is 10 ohms. We have a resistance R2, which is 20 ohms. Join up the circuit. We take the output across the 20 ohms, and I want to know what is that output voltage. Well, we go back and remember what the formula was. Output voltage is input voltage times R2 over R1 plus R2. So I'll just rewrite that. Output voltage is input voltage into R2 over R1 plus R2. This, of course, is R1, this is R2. So the output voltage, which is what we want to find, is the input voltage, which is 9 volts, times R2, which is 20, divided by R1 plus R2, so that's 10 plus 20 is 30. So 20 over 30 is 2/3. 2/3 of 9 is 6 volts. So the output voltage is 6 volts. That means I could put a 6 volt filament lamp, or indeed a 6 volt anything rated as 6 volts across that output, and I could drive it with a 9 volt battery. Ordinarily, if I just put that component across the 9 volt battery, it would burn out. But under this arrangement, I've got a lower voltage because I've used what's called a potential divider. I've divided up this potential into 2 chunks. This chunk I don't really care about. This is the chunk where I need the output. In an earlier video on this series in electricity at GCSE level, we came across 2 components. One was called a thermistor, and another was called a light-dependent resistor. Now, in each case, the resistance of these components varies. In the case of the thermistor, the resistance varies according to temperature. And the idea is that when it's very cold, the resistance is high. When it's hot, the resistance is low. It's not a straight line, it curves. But essentially this is cold and this is hot. So this is a measure of temperature, increasing temperature. And it's high resistance when it's cold, low resistance when it's hot. The light dependence resistor is a similar sort of thing. The resistance is here, but this time it's light. So it's dark at this end, it's light at that end, it's increasing light along the bottom. And what happens is it's a high resistance when it's dark, it's a low resistance when it's light, and it's joined something like this. So suppose we put one of those devices, we'll take a thermistor, but it would work equally well with the other one. Incidentally, the symbols in the circuit, just to remind you, in the case of a thermistor, the symbol looks like this. In the case of a light-dependent resistor, the symbol looks something like this, with the light coming in. Oh gosh, the light coming in, That's the thermistor, that's the light-dependent resistor. And what I'm going to do is to put a thermistor in the potential divider circuit. But in this case, I'm going to make that R1. So here's my battery. Here is my thermistor. And that's R1. And then here is an ordinary resistance, R2. And as before, I'm going to take the output across R2. So that is V out, and this is V in. Just remind you what the, make that clearer. Let's just remind you that the formula is that V out is equal V in times R2 over R1 plus R2. So let's look and see what that voltage, that output voltage will be dependent on, since we've got a thermistor in the circuit, it's this graph we're going to be looking at, whether it's cold or whether it's hot. We'll start off with it cold. If it's cold, V0 will be Vi times R2 over R1 plus R2. Now, R2 is set at a reasonably small resistance, so it's a small value. If it's cold, R1, which is the thermistor, will be a very high resistance. So, we're going to get R2, which is small, divided by R1, which is large, plus a small number. Well, a large number plus a small number is still a large number. So we've got a small number divided by a very large number. That fraction is of the order of 0. It's not quite, but it's very, very small, which means that the output voltage will be Vi times a number that is approaching 0. That's going to be of the order of 0 volts. Very small voltage, if not 0, of the order of 0. Now let's look and see what happens when it's hot. Well, V0 will equal Vi times this fraction. But what is this fraction? Well, now you've got a very, very low resistance because it's hot. So you've got R2, which is a small number, divided by R1 plus R2, where R1 will be very, very much smaller than R2. So in essence, you've got R2 divided by a number that is very close to R2. Essentially, you've got R2 divided by R2 because R1 is making virtually no impact. R2 over R2 is 1. Consequently, the output voltage will equal the input voltage times 1. So VO, the output voltage, equals Vi, the input voltage. So when it's cold, the output voltage is pretty close to 0. When it's hot, the output voltage is pretty close to the input voltage, which depending on the size of the battery could be 9 volts if you're using a 9-volt battery. So you've got output voltage 0 volts when it's cold, output voltage of 9 volts when it's hot, and what you do is you connect this to a logic board. Now we haven't yet done logic boards, but what logic boards are very good at is telling the difference between the voltages. So what you would have, and incidentally not only telling the difference but doing something as a consequence. So the logic board would be set up to say, if the output voltage is of the order of 0 volts, that means it's cold, that means you must switch the central heating on. The logic board would also say, if the output voltage is of the order of 9 volts, or whatever the input voltage happens to be, that means it's hot. That means you switch the central heating off. And the same would apply with the light-dependent resistor. If the resistance is very high, that means the output voltage will be 0. That means it's dark. That means switch the light on. If the resistance of the light-dependent resistor is very low, that means it's light. That means you'll get an output voltage which is equal to the input voltage or thereabouts. As I've said, that means it's light. That means you can switch the outside light off.